Have you ever looked up at the night sky and felt like there's something more to it, something hidden, something waiting to be understood? The universe isn't just a random scattering of stars and galaxies. It's woven with patterns, secrets tucked into the fabric of space and time, clues that scientists and thinkers have been chasing for centuries. Some of these patterns are so subtle, so elusive, that they feel like whispers from the cosmos itself. And what if I told you these whispers might hold the answers to some of the biggest questions we've ever asked? From the spiraling arms of galaxies to the strange symmetries in quantum physics, the universe seems obsessed with repetition, with order emerging from chaos. Ancient civilizations saw these patterns and built myths around them. Modern astronomers measure them with telescopes and supercomputers. But no matter how far we've come, the deeper we look, the more mysteries we uncover. That's what makes this journey so thrilling, because every discovery doesn't just solve a puzzle, it reveals 10 more, each more fascinating than the last. In this video, we're diving into 30 of the most compelling theories about the hidden patterns of the universe. Some will sound like science fiction. Others might make you question everything you thought you knew. But all of them share one thing: their attempts to decode the cosmic blueprint, to find the underlying rules that make our universe tick. Whether it's the eerie perfection of the Fibonacci sequence in nature, the bizarre behavior of black holes, or the mind-bending idea that we might live in a hologram, these theories are the frontier of human curiosity. So if you've ever wondered what's really going on out there beyond the stars, beyond what we can see, stick around. Because the universe has been leaving clues for us, and it's time we started putting them together. One of the most mesmerizing patterns in nature isn't just here on Earth. It's written across the cosmos itself. The Fibonacci sequence, that elegant series of numbers where each one is the sum of the two before it, shows up in places you'd never expect. Take a spiral galaxy, for instance. Its swirling arms don't just curve randomly. They follow the same logarithmic spiral found in seashells, hurricanes, and even the way leaves unfurl from a stem. The numbers behind this pattern, 1, 1, 2, 3, 5, 8, and so on, seem to whisper a universal truth about growth, efficiency, and balance. But why would galaxies, vast beyond comprehension, obey the same mathematical rules as a sunflower? Some researchers think it's no accident. The Fibonacci sequence emerges from something called the golden ratio, a proportion so perfect it appears in everything from ancient architecture to the proportions of our own bodies. When cosmic structures form, the forces of gravity and rotation might naturally favor this efficient, harmonious arrangement. It's as if the universe has a favorite shape, one that minimizes chaos and maximizes stability. Even planetary orbits, when you look closely, sometimes echo these ratios with resonant patterns that keep celestial bodies in sync. Not everyone agrees, of course. Skeptics argue that while the sequence is beautiful, it might just be a happy coincidence, a case of humans seeing patterns where none truly exist. But here's the thing: when something appears this often, from the tiniest fern to the grandest galaxy, it's hard to dismiss as mere chance. Whether it's a fundamental law or just a curious quirk, the Fibonacci sequence reminds us that the universe might be far more orderly and far stranger than we ever imagined. The golden ratio, often called nature's perfect number, shows up in places so unexpected, it's hard to believe it's just coincidence. Picture this: the spiraling arms of a galaxy, the curve of a nautilus shell, even the branching of trees, all following this same exact proportion, roughly 1.618 to 1. Ancient mathematicians like Euclid called it the extreme and mean ratio, but it's more than just a math trick. The Egyptians built the Great Pyramid with its sides aligned to this ratio, and the Greeks sculpted the Parthenon's columns to mirror its perfection. To them, this wasn't just aesthetics, it was sacred, a bridge between the earthly and the divine. What's fascinating is how deep this pattern goes. At the atomic level, the spacing between electron orbitals sometimes echoes the golden ratio. In space, the arrangement of planets and moons occasionally falls into resonant orbits that reflect these same proportions. Even the human body follows it, the length of your forearm compared to your hand, the spiral of your inner ear, even the way your DNA coils. It's as though the universe has a favorite blueprint, one it keeps returning to no matter the scale. But why would something so precise appear everywhere? Some scientists argue it's simply the most efficient way for things to grow and organize, a natural solution to packing structures tightly or optimizing energy flow. Others wonder if it hints at something deeper, a fundamental law we haven't fully uncovered yet. Skeptics point out that not every spiral or ratio matches perfectly, but the sheer frequency is hard to ignore. Whether it's a cosmic accident or a hidden rule, the golden ratio challenges us to look closer, because if the universe keeps signing its work with the same number, maybe we're meant to pay attention. If the Fibonacci sequence hints at cosmic order, then fractals are the universe's way of showing off its obsession with repetition, down to the tiniest detail. Imagine zooming in on a jagged coastline, a bolt of lightning, or the branching veins of a leaf. No matter how close you get, the same intricate patterns keep reappearing, like a hall of mirrors reflecting infinity. This isn't just artistic flair, it's fractal geometry, a mathematical language where simple rules create infinitely complex shapes, and it doesn't stop at Earth. From the distribution of galaxies to the swirls of cosmic dust, the universe seems to build itself using these recursive blueprints. The man who cracked this code was Benoit Mandelbrot, a mathematician who asked a deceptively simple question: how long is the coast of Britain? The answer, he realized, depends on how closely you measure. At every scale, from satellite view to a grain of sand, the edges reveal more twists and turns, making the true length unknowable. This led him to the Mandelbrot set, a dizzying fractal where infinite complexity emerges from just one equation. Zoom into its spiraling edges, and you'll find smaller versions of the whole, a cosmic nesting doll that never ends. What's staggering is how these patterns govern reality. Rivers branch like fractal trees, lungs expand with fractal airways to maximize surface area, and even stock market fluctuations trace fractal rhythms. But step back, and the same rules apply to the cosmos. Galaxy clusters aren't randomly scattered. They form web-like structures where filaments of matter stretch across unfathomable distances, mirroring the branching of roots or neurons. Some scientists speculate that fractal geometry could be the key to quantum gravity, a way to bridge the chaos of the very small with the smoothness of spacetime. Not everyone sees this as proof of a grand design. Critics argue fractals are just efficient nature's shortcut for building complexity from simplicity. Yet the eerie precision suggests something deeper. If the universe repeats its patterns from quark to quasar, could infinity itself be woven into the fabric of reality? Whether it's math or metaphysics, fractals force us to rethink scale. After all, if a single equation can generate endless beauty, maybe the cosmos isn't just vast, it's infinitely creative. The cosmic microwave background, often called the universe's baby picture, should be smooth, a nearly perfect snapshot of the early cosmos. But when scientists mapped it in exquisite detail, they found something unsettling. Scattered across this ancient light are strange imperfections, patches where the temperature dips or spikes in ways no one predicted. The most infamous of these is the so-called cold spot, a region of space chillingly colder than its surroundings by a margin that defies standard physics. At first glance, it might seem like a glitch, a statistical hiccup in the data. Dig deeper, though, and this anomaly, along with others like it, might be whispering secrets about realities beyond our own. Some researchers suspect these irregularities could be bruises left by a collision with another universe. Imagine our cosmos as one bubble in an endless foam of universes, each with its own laws of physics. If another bubble brushed against ours in the unimaginable chaos of the multiverse, the energy of that impact might have left a mark, a cold spot frozen in time. It's a wild idea, but not without precedent. The math of inflationary theory, which explains the universe's rapid expansion after the Big Bang, actually predicts the possibility of such collisions. If true, then that cold spot isn't just a curiosity, it's a fingerprint from a reality we can never otherwise see. Not everyone's convinced, of course. Skeptics argue that the cold spot could simply be a trick of perspective, an illusion caused by a vast void, a cosmic emptiness stretching millions of light years, where the lack of galaxies subtly distorts the CMB. Others suggest it might be evidence of pre-Big Bang physics, relics from whatever existed before time as we know it began. Whatever the explanation, these anomalies force us to confront how little we truly understand about the universe's origins. What makes the CMB's mysteries so tantalizing is their scale. This isn't some subtle quirk in a lab experiment. It's a flaw woven into the fabric of the entire observable universe. If these irregularities are signs of the multiverse, they'd be the first tangible evidence that our cosmos isn't alone. But if they're just statistical noise, they'd still challenge our models of how the universe evolved. Either way, the CMB isn't just a relic, it's a riddle, one that keeps cosmologists awake at night, wondering if they're staring at the edge of reality itself. There's something out there in the cosmic dark, an unseen force so powerful it's dragging entire galaxies toward it like a cosmic whirlpool. Astronomers call it the Great Attractor, and it's one of the most baffling mysteries in modern cosmology. Hidden behind the dust and stars of our own Milky Way, this gravitational behemoth tugs at everything in our galactic neighborhood, pulling thousands of galaxies toward a single point in space with irresistible force. But what is it? The answer might rewrite our understanding of the universe itself. At first, scientists thought it could be a colossal cluster of galaxies, their combined gravity bending the fabric of space-time. But when they peered through the obscuring veil of the Milky Way's disk, what they found didn't add up. The mass they detected, while enormous, wasn't nearly enough to explain the sheer strength of the pull. That's when the theories got wild. Some speculate it's a supercluster we can't fully see yet, a sprawling metropolis of galaxies shrouded in cosmic dust. Others propose it's evidence of dark flow, a controversial idea suggesting that something beyond the observable universe, perhaps an unimaginably massive structure or even another universe, is exerting its gravitational influence on us. Then there's the supervoid theory. Imagine a vast, nearly empty region of space, a bubble so devoid of matter that it creates a kind of gravitational deficit. Galaxies on the far side of this void would appear to be pulled toward it, not because the void itself has gravity, but because the lack of gravity elsewhere makes it seem that way. It's like standing on a slope where one side suddenly drops away. You'd naturally slide toward the dip. But even this elegant explanation struggles to account for the scale of the Great Attractor's pull. The most tantalizing possibility that we're feeling the tug of a parallel universe. If our cosmos is just one bubble in an endless multiverse, and another bubble drifted close enough, its gravity could leak into ours, warping space-time on a scale we can't yet comprehend. It sounds like science fiction, but some versions of string theory actually allow for this kind of interaction between universes, of course, proving it is another matter entirely. What makes the Great Attractor so thrilling is how it humbles us. Even with our most advanced telescopes and supercomputers, we're still piecing together the puzzle of our own cosmic backyard. Every time we think we've got the universe figured out, it throws another curveball, and this one might be the biggest yet. Whether it's hidden mass, a flaw in our understanding of gravity, or a doorway to another reality, the Great Attractor reminds us that the universe is always holding a few cards close to its chest. Sometimes the universe doesn't just hide its secrets, it seems to taunt us with them. Take the so-called axis of evil, a bizarre pattern in the cosmic microwave background that shouldn't exist. According to everything we know about the Big Bang, the early universe was a hot, chaotic soup, expanding uniformly in all directions. The afterglow of that explosion, the CMB, should be evenly splattered across the sky like paint flicked onto a canvas. But it's not. Instead, scientists found something unsettling. The largest scale fluctuations in the CMB aren't random. They're aligned along a peculiar axis, as if the universe has a hidden North Star guiding its structure. This alignment, dubbed the axis of evil by a skeptical researcher, defies the cosmological principle, the bedrock idea that the universe looks the same in all directions on large scales. The quadrupole and octupole moments, fancy terms for specific patterns in the CMB's temperature variations, point eerily toward the same slice of space, like compass needles all swinging toward some invisible magnet. Even stranger, this axis roughly lines up with the plane of our solar system and the direction Earth moves through the cosmos. That's either a jaw-dropping coincidence or a sign that something's profoundly wrong with our models. One camp argues it's an artifact, a ghost in the data. Maybe our telescopes are picking up contamination from dust in the Milky Way, or perhaps the way we process the measurements introduces subtle biases. Others think it could hint at a cosmic anomaly, like a universe that's not quite isotropic, where one direction holds more weight than others. The wildest theories suggest this axis might trace back to the pre-Big Bang era, a relic of some asymmetric inflation that twisted spacetime itself. Imagine the universe not as a perfectly blown-up balloon, but as one slightly pinched at the edges, its expansion lopsided from the very beginning. Then there's the really radical idea that we're seeing fingerprints of a multiverse. If our universe is one bubble among many, neighboring bubbles could imprint their presence on ours, leaving behind gravitational echoes that nudge the CMB into alignment. It's like finding a gust of wind in a sealed room, evidence of something outside we can't yet see. But here's the twist: the axis of evil might not be evil at all. What if it's a clue, a cosmic breadcrumb leading us to a deeper truth? After all, every time science has stumbled on an anomaly, from Mercury's wonky orbit to the expansion of the universe, it's forced us to rewrite the rules. Whether this alignment is a flaw in our maps or a feature of reality, it's a reminder that the universe doesn't owe us symmetry, and that's what makes it so thrilling. Because if the cosmos has a preferred direction, it's not just breaking the rules, it's inviting us to discover new ones. Quantum entanglement is one of those ideas that feels ripped straight from science fiction, particles separated by vast distances instantly influencing one another, as if space and time don't exist between them. Here on Earth, we've demonstrated this phenomenon in labs, with photons or electrons entangled so that measuring one instantly determines the state of its partner, even if they're on opposite sides of the planet. But what if this bizarre connection isn't just a quirk of tiny particles? What if it's a cosmic blueprint, a hidden thread stitching the universe together at the grandest scales? The wildest part, quantum entanglement, might not stop at the atomic level. Some theorists suspect it could be the missing link between quantum mechanics and gravity, two frameworks that stubbornly refuse to play nice in our equations. Picture this: just as entangled particles share a bond that defies distance, the fabric of spacetime itself could be woven from similar invisible connections. Black holes, those cosmic vacuum cleaners, might hold clues. When matter falls into a black hole, its information doesn't just vanish. It's theorized to be scrambled and preserved on the event horizon, the point of no return. Meanwhile, particles escaping as Hawking radiation could remain entangled with what's inside. This creates a paradox. How can two things be connected when one's trapped in a black hole and the other's racing across the cosmos? The answer might lie in something called ER equals EPR, a brain-twisting idea from quantum physics. It suggests that entangled particles could be linked by microscopic wormholes, tiny bridges through spacetime. If true, entanglement isn't just a curious link between particles, it's a physical tunnel, a hidden structure woven into reality itself. Now zoom out. If spacetime is built from countless quantum entanglements, it's like the universe is an unfathomably vast network, with every star, galaxy, and atom subtly tethered together in ways we're only beginning to glimpse. But here's where it gets even stranger. If entanglement scales up, could entire galaxies be entangled? Imagine two distant galaxy clusters mirroring each other's movements, not because of gravity alone, but because they share a quantum bond deeper than spacetime. It sounds impossible, but so did quantum mechanics a century ago. Skeptics argue that decoherence, the tendency for quantum systems to unravel in noisy environments, would prevent such large-scale entanglement. Yet others counter that the vacuum of space might be pristine enough to preserve these fragile connections over cosmic distances. The implications are staggering. If quantum entanglement truly underlies gravity, it could finally unite Einstein's relativity with quantum theory, the holy grail of physics. It would mean that the universe isn't just held together by warped spacetime, but by an invisible web of quantum ties, a hidden architecture we're only now learning to map. And if we ever crack this code, we might not just understand gravity, we might find that the cosmos is far more connected, far more mysterious than we ever dreamed. What if everything you see, the stars, the planets, even your own hands, is just an illusion? That's the mind-bending premise of the holographic principle, a theory so radical it suggests our three-dimensional universe might actually be a two-dimensional projection, like a cosmic hologram. At first glance, the idea sounds like something straight out of a sci-fi novel, but dig deeper and you'll find it's rooted in some of the most cutting-edge physics, born from a paradox that's haunted scientists for decades. What happens to information when it falls into a black hole? The story starts with a puzzle Stephen Hawking uncovered in the 1970s. Black holes, he realized, aren't just cosmic vacuum cleaners, they evaporate over time, leaking energy known as Hawking radiation. But here's the catch: if a black hole vanishes, what happens to all the stuff it swallowed? Quantum mechanics insists information can't be destroyed, yet general relativity says it's gone forever. This contradiction, dubbed the black hole information paradox, seemed unsolvable until a pair of physicists proposed a wild way out. Maybe the information isn't lost. Maybe it's painted on the black hole's event horizon, the surface marking its point of no return. Think of it like a cosmic prison wall. Every atom, every photon that falls in leaves a two-dimensional imprint, a sort of ultra-dense barcode storing its quantum details. Now stretch this idea to the entire universe. If a black hole's contents can be encoded on its boundary, could reality itself be a projection from some distant, flat surface? That's the holographic principle in a nutshell. It's as if the universe is a giant movie screen and everything we experience, the depth, the texture, the sense of space, is just light and shadow playing across its surface. The math even checks out. The equations describing physics in a three-dimensional space can sometimes be rewritten as equivalent theories operating in two dimensions, with no loss of information. It's like discovering that a sprawling, intricate novel can be perfectly summarized in a single haiku. But how could this possibly work? Imagine a hologram on your credit card, tilt it, and the flat surface gives the illusion of depth. The holographic principle suggests spacetime does something similar, with every event, every particle arising from interactions on some distant, two-dimensional boundary we can't see. Some versions of the theory even pinpoint this boundary as the edge of the observable universe, a cosmic horizon where information is stored like pixels on a screen. Of course, not everyone's convinced. Critics argue that while the math is elegant, there's no direct evidence yet that we're living in a hologram. Others counter that the principle might not mean the universe is two-dimensional, but that it behaves like it is under certain extreme conditions, like near a black hole's edge. But here's the tantalizing part. If the holographic principle is true, it could solve one of physics' biggest headaches: quantum gravity. By treating space-time as an emergent property, bubbling up from deeper, simpler rules, we might finally bridge the gap between the quantum world and Einstein's relativity. What makes this theory so electrifying isn't just the science, it's the poetry. The idea that every supernova, every galaxy, even your thoughts right now, might be the shimmering reflection of data etched on the edge of reality feels like something from ancient myth. But that's the beauty of cosmology. The universe's deepest truths often sound like magic until we uncover the equations hiding behind the curtain. Whether the holographic principle holds up or not, it challenges us to rethink the very nature of existence. After all, if reality is just a projection, who or what is holding the projector? What if the universe isn't just governed by mathematics? What if it is mathematics? That's the unsettling heart of the simulation hypothesis, the idea that everything we see, touch, and experience might be nothing more than lines of code running on some unfathomably advanced computer. Think about it. The universe operates with eerie precision, from the orbits of planets to the behavior of subatomic particles, all following mathematical laws so exact they feel like programmed rules. Even space itself might have a resolution: Planck lengths, the tiniest possible units of distance, acting like cosmic pixels. If that doesn't make you pause, consider this: reality glitches sometimes. Particles pop in and out of existence, quantum states remain unresolved until observed, and black holes erase information. Could these just be bugs in the system? Philosopher Nick Bostrom framed this idea as a trilemma: three stark possibilities, at least one of which must be true. First, almost all civilizations at our level go extinct before developing simulation technology. Second, if they do advance, they almost never choose to run ancestor simulations, virtual worlds mimicking their past. Or third, we're almost certainly living in one of those simulations right now. The logic is chilling. If even a tiny fraction of civilizations survive and create simulated realities, the number of artificial universes would dwarf the one real cosmos. Statistically, the odds we're in the original reality start to look vanishingly small. Elon Musk famously put it this way: the odds we're in base reality is 1 in billions. But let's poke at the evidence. The universe's mathematical underpinnings are suspiciously tidy. Why do fundamental constants like the speed of light or the strength of gravity have such perfect, life-allowing values? Slight tweaks would make stars, planets, or even atoms impossible. Simulation theorists argue it's like a video game designer fine-tuning parameters to keep players engaged. Even quantum indeterminacy, the way particles exist in probability clouds until measured, could mirror a system conserving processing power, only rendering details when observed. And those Planck lengths, they're the smallest meaningful units in physics, a limit that hints at a universe running on finite computation. Not everyone's buying it. Critics counter that just because reality can be described mathematically doesn't mean it's artificial. The laws of physics might simply be the way they are because any other arrangement wouldn't allow complexity or us to exist. This is the anthropic principle. We observe the universe's fine-tuning because we couldn't observe it otherwise. As for glitches, quantum weirdness and information paradoxes might just reflect gaps in our knowledge, not proof of a digital facade. The wildest twist: there's no way to definitively disprove the simulation hypothesis. Any test we devise could theoretically be part of the program, but some physicists have proposed looking for compression artifacts, cosmic shortcuts a lazy programmer might take. Maybe high-energy particles behave oddly at the edges of the observable universe, or mathematical inconsistencies lurk in uncharted physics. Others suggest we might one day find the universe's source code buried in the laws of quantum mechanics, like Easter eggs left by a playful designer. Whether you find the idea thrilling or terrifying, the simulation hypothesis forces us to confront a profound question. What does real even mean? If consciousness can emerge from circuits as easily as from neurons, does it matter if our universe is silicon or stardust? And if we are in a simulation, who's to say our creators aren't also someone else's simulation? It's turtles or code all the way down. One thing's certain: if reality is a game, we're all playing on hard mode with no cheat codes in sight. The universe isn't just held together by the stars and galaxies we see, it's woven into shape by something invisible, a ghostly skeleton we can only detect by its gravitational pull. Dark matter, the mysterious substance making up roughly 85% of all matter in the cosmos, doesn't emit or reflect light. Yet without it, galaxies would fly apart and the universe as we know it wouldn't exist. The strangest part, this unseen material isn't just floating around randomly. It forms an intricate, sprawling web, a cosmic scaffold stretching across billions of light years, with galaxies clustering along its filaments like pearls on a string. Picture the universe as a vast ocean and dark matter as the currents beneath the surface, silently guiding everything above. Supercomputer simulations reveal this hidden framework with stunning clarity. Dark matter condenses into dense threads, intersecting at nodes where galaxy clusters form, leaving vast, empty voids in between. It's a fractal architecture, repeating on scales from the tiniest dwarf galaxies up to the largest structures we've mapped. But if we can't see it, how do we know it's there? The answer lies in gravity's tricks. Light bending around galaxy clusters' gravitational lensing reveals the invisible mass distorting spacetime. Stars orbit the centers of galaxies too fast for visible matter alone to hold them. Without dark matter's grip, spiral arms would unravel and star clusters would scatter into the void. So what is this elusive stuff? The leading candidate is WIMP, weakly interacting massive particles. These hypothetical particles barely touch ordinary matter, slipping through our planet like ghosts. If they exist, detectors buried deep underground might one day catch a rare collision. But after decades of searching, WIMP remain frustratingly out of reach. That's led some scientists to flirt with another idea: actions. Unlike WIMP, these ultralight particles could behave more like waves, their collective dance generating the gravity we attribute to dark matter. Actions are poetic in a way. They were originally dreamed up to solve a completely unrelated puzzle in quantum physics, only to resurface as cosmic contenders. Then there's the radical alternative: maybe dark matter doesn't exist at all. Modified Newtonian dynamics, or MUND, suggests we've misunderstood gravity itself. At galactic scales, tiny tweaks to Newton's laws could explain the strange motions of stars without invoking invisible mass. It's an elegant solution except for one snag. When galaxies collide, the visible matter and gravitational pull don't always line up. In the Bullet Cluster, for instance, two galaxies have slammed through each other, leaving their gas clouds behind like cosmic wreckage. The gravity, though, stayed centered where the stars are, hinting at an unseen mass lagging in the middle. For MUND supporters, this is a headache. For dark matter believers, it's Exhibit A. The debate isn't just academic. Unraveling dark matter's identity could rewrite the rules of particle physics, revealing entirely new forces or dimensions. Or it might force us to rip up Einstein's playbook and rethink gravity from scratch. Either way, the invisible web isn't just holding galaxies together. It's pulling us deeper into the mystery, reminding us that the universe's greatest secrets aren't always written in light. Dark energy is the universe's greatest magic trick, an invisible force that's not just pushing galaxies apart but doing it faster and faster, as if space itself has a hidden accelerator pedal. When astronomers first discovered this in the late 1990s, it shattered expectations. Everyone assumed gravity would slow the cosmic expansion, the way a ball tossed upward gradually loses speed. Instead, distant supernova revealed the opposite. The universe is speeding up, stretching spacetime like taffy with no sign of stopping. the culprit. Something we can't see, can't touch, but makes up nearly 70% of everything, dark energy. The simplest explanation is Einstein's old fudge factor, the cosmological constant. Back in 1915, he inserted this term into his equations to keep the universe static, calling it his biggest blunder when Edwin Hubble proved everything was moving apart. But now it's back with a vengeance. The cosmological constant suggests empty space isn't really empty, it seethes with latent energy, a kind of background hum that generates repulsive gravity. The more space expands, the more of this energy appears, creating a runaway effect. It's elegant, but there's a snag. Quantum predictions for the cosmological constant strength are off by a jaw-dropping 120 orders of magnitude. That's like expecting a whisper and getting a supernova. Enter quintessence, a more exotic fix, named after the ancient fifth element. This theory proposes dark energy isn't constant at all. It's a dynamic field, ebbing and flowing over time. Picture it like an invisible tide, sometimes pushing harder, sometimes weaker. If true, it could explain why dark energy's influence seems to have kicked in late, letting galaxies form before the expansion took over. But quintessence has its own headaches. It requires a finely tuned, unexplained particle or field, something we've never detected. Worse, some versions predict a nightmarish Big Rip scenario. In this fate, dark energy grows so strong it overwhelms all fundamental forces. First galaxies tear apart, then stars, planets, eventually atoms themselves are shredded in a final, apocalyptic instant. The stakes couldn't be higher. If dark energy behaves like the cosmological constant, the universe will expand forever, galaxies vanishing over the horizon until each is alone in an icy void. If it's quintessence, the future could be a roller coaster, maybe even a collapse. And if the Big Rip is real, well, cosmic doomsday has a new frontrunner. What makes dark energy so maddening is how little we grasp about it. We're like ants trying to understand wind by watching leaves move. Upcoming telescopes like the Vera Rubin Observatory might spot clues in the way distant galaxies distort light or how clusters grow over time. But for now, dark energy remains the universe's biggest question mark, a reminder that the cosmos isn't just expanding, it's running away from us and we're left chasing shadows. Imagine waking up one day, convinced you're a real human in a real world, only to discover you're just a fleeting spark of consciousness, a random accident in an endless sea of chaos. That's the spine-chilling premise of the Boltzmann brain paradox, a thought experiment that turns our understanding of reality inside out. It starts with a simple question. In an infinitely old or infinitely vast universe, how do we know we're not just temporary glitches? The idea traces back to Ludwig Boltzmann, a 19th century physicist who grappled with entropy, the universe's tendency toward disorder. He realized that given enough time, even the most improbable events become inevitable. In a cosmos trillions upon trillions of years old, particles jostling at random could, by sheer chance, arrange themselves into a functioning, self-aware brain, complete with fake memories of a life that never happened. According to this logic, it's statistically more likely you're one of these Boltzmann brains, briefly flickering into existence, than an actual person in an ordered universe. Here's where it gets even stranger. Modern cosmology suggests our universe might be headed for a heat death, a state where all energy is evenly spread out and nothing happens forever. But in that vast expanse of nothingness, quantum fluctuations could still spawn pockets of order. A Boltzmann brain wouldn't need a body or a world, just the right arrangement of particles to create the illusion of both. And if that's possible, then over infinite time, there would be countless more Boltzmann brains than real, evolved beings like us. So statistically speaking, what are the odds you're the exception? Some physicists dismiss this as a reductio ad absurdum, a flaw in our models, not a genuine possibility. If the universe is truly infinite, shouldn't we also see random floating TVs or fully formed cities popping into existence? Others argue it's a warning sign that our theories are missing something crucial, like how quantum gravity might prevent such absurdities, the real kicker. There's no way to prove you're not a Boltzmann brain. Any memory or observation you use as evidence could itself be part of the illusion. But here's the twist: the paradox might reveal a deeper truth about reality's structure. Maybe the universe needs observers not as accidents but as fundamental to its existence. Or perhaps consciousness isn't just a byproduct of particles, but something woven into the fabric of space-time itself. Whether a disturbing glitch or a clue to something grander, the Boltzmann brain forces us to confront the fragility of our assumptions. After all, if reality can't be trusted, what's left to hold onto? Maybe just this: even if we're fleeting, the questions we ask are real enough, and that's what makes us human, not just ghosts in the cosmic machine. Time crystals sound like something straight out of a physicist's dream. Structures that don't just exist in space but pulse rhythmically in time, forever locked in a dance that defies entropy itself. Unlike ordinary crystals, where atoms arrange in repeating patterns like a grid, time crystals take it a step further. Their atoms oscillate between states in a never-ending cycle, like a clock that ticks without any energy input, forever resisting the universe's relentless slide toward disorder. The idea was so outlandish that when Nobel laureate Frank Wilczek first proposed it in 2012, many dismissed it as impossible. But just 5 years later, labs created them, proving reality could be stranger than fiction. How do these bizarre structures work? Imagine pushing a swing just once. Normally, it would gradually slow to a stop, but in a time crystal, the swing keeps rocking back and forth indefinitely. Not because you keep pushing it, but because the system remembers the push, locked in a quantum loop of perfect repetition. This happens thanks to a phenomenon called many-body localization, where quantum particles get stuck in a kind of traffic jam, unable to share energy with their surroundings. The result: a structure that flips between states with clockwork precision, not in space but in the dimension of time itself. Now zoom out to cosmic scales. If tiny lab-made time crystals can resist entropy, could the universe have birthed its own natural versions in the extreme conditions of the early cosmos? Some theorists speculate that time crystals might have formed moments after the Big Bang, when the fabric of reality was still settling into place. These ancient relics, if they exist, could be humming along even now, hidden in the depths of space, their oscillations undisturbed for billions of years. They might even hold clues about the universe's infancy, like fossils but frozen in time rather than stone. But the wildest idea: time crystals could be the scaffolding of perpetual cosmic cycles. Some interpretations of quantum gravity suggest that spacetime itself might emerge from a deeper, more fundamental layer of reality, one where time crystals play a role in stitching together the fabric of existence. Picture the universe as a grand symphony, with time crystals as its metronome, ticking beneath the surface, guiding the rhythms of expansion and decay. If true, they might not just defy entropy, they could be the reason reality has structure at all. Of course, not everyone's convinced. Skeptics argue that lab-made time crystals are fragile, requiring carefully controlled conditions to survive. Scaling them up to cosmic proportions might be pure fantasy. Others counter that the early universe was a playground for exotic physics, and if any environment could birth such oddities, it was then. Whether relics of creation or just curiosities of quantum mechanics, time crystals force us to rethink one of physics' most sacred laws, that everything eventually must wind down. The fact that they exist at all is a whisper that maybe, just maybe, eternity isn't as impossible as we thought. Black holes have long been cosmic paradoxes, regions where the laws of physics as we know them break down. But perhaps nothing has caused more headaches for physicists than the question of what happens to information that falls into one. According to quantum mechanics information, the detailed state of every particle can never truly be destroyed. Yet black holes with their monstrous gravity seem to erase it completely. This contradiction, known as the black hole information paradox, has sparked a battle of ideas spanning decades, and the stakes couldn't be higher. If information can vanish, our understanding of reality might need a complete rewrite. The trouble started when Stephen Hawking made a startling discovery in the 1970s. Black holes aren't eternal. They slowly leak energy, a phenomenon now called Hawking radiation, fading away over unimaginable timescales. But here's the catch: this radiation appears random, carrying no trace of the matter that originally fell in. It's like burning a library and claiming the smoke patterns contain all the book's information, a notion quantum mechanics flatly rejects. This led Hawking to a radical conclusion. Information really is destroyed inside black holes, violating one of physics' most sacred principles. The backlash was immediate. If Hawking was right, quantum theory, the foundation of everything from chemistry to computers, would crumble. Enter the holographic principle, a daring workaround that flips the script. Maybe information isn't lost. Maybe it's encoded on the black hole's event horizon, the boundary where gravity becomes inescapable. Picture this: as an object plunges toward a black hole, its details get smeared across the horizon like a cosmic fingerprint, preserved in 2 dimensions rather than 3. The mathematics even suggests this. The amount of information a black hole can hold scales with its surface area, not its volume. This bizarre idea implies that our 3-dimensional reality might somehow emerge from a 2-dimensional boundary, like a hologram projecting depth from flat data. Suddenly, the paradox isn't about destruction, it's about translation, a cosmic game of encoding and decoding. But another theory throws gasoline on the fire: the firewall hypothesis. If information does escape via Hawking radiation, quantum mechanics demands a nightmarish consequence. At the event horizon, particles separating from their entangled partners would create a wall of searing energy, an incandescent barrier that would vaporize anything crossing it. This contradicts Einstein's general relativity, which predicts you'd float peacefully past the horizon, blissfully unaware of your doom until tidal forces shred you apart. So which is it, a smooth descent into oblivion or a fiery cosmic griddle? The debate rages, with some physicists suggesting both can't be true, meaning one of our most cherished theories must be wrong. What makes this paradox so electrifying isn't just the science, it's the philosophical whiplash. If information survives, reality might be a holographic projection, with black holes as cosmic archivists. If it doesn't, the universe has a glaring loophole in its rulebook. And if firewalls are real, our understanding of space-time is fundamentally flawed. Every proposed solution peels back another layer of mystery, revealing how little we truly grasp about the fabric of existence. Black holes aren't just cosmic vacuum cleaners. They're the ultimate test labs for the laws of physics, pushing us to confront the unsettling possibility that reality might be stranger and more intricate than we ever imagined. What if our universe is just one bubble in an endless cosmic froth, floating alongside countless others, each with its own unique set of physical laws? This isn't science fiction, it's a serious prediction of eternal inflation, a theory that reshapes how we think about reality's grand design. Picture the Big Bang not as a one-time explosion, but as a never-ending process where space expands exponentially, sprouting new universes like bubbles in a boiling pot. Each of these bubbles could cool into its own distinct cosmos, with different constants, particles, even dimensions. Some might have gravity so weak it can't hold galaxies together. Others might crackle with forces we've never seen. And in this infinite sea of possibilities, the patterns we consider fundamental, the Fibonacci spirals, the golden ratio, the fractal webs of dark matter, might be nothing more than local quirks, accidents of our particular bubble's physics. The math behind eternal inflation is as elegant as it is mind-bending. In the seething quantum foam of the early universe, patches of space could have gotten stuck in high-energy states, driving runaway expansion. When these patches finally decayed, they released their pent-up energy, igniting the hot, dense conditions of a Big Bang. But the surrounding space kept inflating eternally, birthing new bubbles ad infinitum. The wildest part, these universes wouldn't just be far away, they'd be entirely disconnected, their space-times causally severed from ours. We could never visit them, never signal them, but their existence might still leave faint traces in our sky. That cold spot in the cosmic microwave background, some theorists argue it's a bruise from our bubble grazing another in the multiverse's foam. Now imagine stepping into one of these alternate realities. A universe where gravity is 10 times stronger might collapse into black holes before stars could even form. One where the electromagnetic force is weaker might never cook up the complex chemistry needed for life. And what if some bubbles have extra spatial dimensions, coiled so tightly we'd never notice, or one so vast that planets orbit in hypercubes instead of spheres? The sheer variety is dizzying, but here's the kicker. In an infinite multiverse, every conceivable configuration must exist somewhere. There's a version of reality where you're reading this script upside down, another where time flows backward, and infinitely more where the laws of physics render life, or even matter, impossible. Critics argue this sounds less like science and more like metaphysics. If we can't observe other universes, how can we test the theory? Supporters counter with a clever twist. The multiverse might explain why our universe seems so finely tuned for life. In a cosmic lottery with infinite tickets, it's no surprise one universe hit the jackpot. But the real question isn't just whether the multiverse exists, it's what hidden patterns might lurk in those alien physics. Could Fibonacci sequences emerge in a universe with 5 fundamental forces? Would dark energy's repulsion still sculpt galactic superclusters if gravity worked differently? The answers could reveal whether math is truly universal or just a happy accident of our local rules. Whether you find the multiverse exhilarating or unnerving, it forces a humbling thought. The symmetries we call laws might be no more universal than the weather on Earth. And if that's true, then every equation we've ever written is just a postcard from our tiny corner of reality, one scribbled note in an infinite library of possibilities. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cycle of cosmic collisions? That's the radical premise of the ekpyrotic universe theory, a model that swaps the singularity for something far stranger. 2 universes slamming into each other in the hidden depths of higher dimensional space. Picture our cosmos not as a lone bubble but as a membrane, or brain floating in a vast, unseen dimension. Now imagine another brain drifting parallel to ours, invisible and untouched until gravity slowly pulls them together. When they collide, the energy of that impact doesn't destroy. It creates, igniting a fiery rebirth that looks to us exactly like the Big Bang. This idea springs from string theory, which suggests reality might have 10 or 11 dimensions, most curled up so tightly we never notice them. In this framework, our universe could be a 3-dimensional brain existing alongside others, like sheets of paper floating in a windless room. The ekpyrotic model takes it further. These brains aren't static. They move, drawn together over eons until crash. Their collision unleashes enough heat and chaos to forge an entirely new cosmos from the ashes. No singularity, no nothingness before time, just an endless cosmic dance of destruction and renewal. How does this differ from the classic Big Bang? For starters, it solves the horizon problem, the puzzle of why distant regions of space look so similar despite never having interacted. Inflation theory patches this by proposing a fleeting period of hyper-expansion. But the ekpyrotic universe offers an elegant alternative. Those regions were in contact, stretched and smoothed during the slow, pre-collision approach of the brains. It also sidesteps the mystery of what triggered the Big Bang. Instead of a singularity appearing from nowhere, the cycle simply resets, with each collision seeding the next universe. But here's where it gets mind-bending. If this model is correct, our universe might bear scars from previous collisions, subtle imprints in the cosmic microwave background, or gravitational waves humming from the depths of space. Some researchers even speculate dark matter could be particles left stranded in the higher dimensional bulk between branes, ghostly remnants of past cycles. And if branes can collide once, why not infinitely? Time itself might be cyclical, with universes rising and falling like breaths, each one subtly different from the last. Critics point out gaps. The math requires branes to approach almost perfectly parallel, a fine-tuning some find as unsatisfying as the Big Bang's initial conditions. Others argue that without observable proof, like unique patterns in the CMB, the theory remains elegant speculation. But for supporters, the appeal is undeniable: a universe without a true beginning or end, where endings are just new beginnings in disguise. After all, if cosmologists have learned one thing, it's that reality loves a good pattern. And what's more poetic than a cosmos that recreates itself over and over in an eternal embrace of fire and gravity? The silence is deafening. After decades of scanning the skies for signals, we've found no definitive trace of extraterrestrial civilizations. No radio broadcasts, no megastructures, not even a single alien probe drifting through our solar system. This eerie absence, known as the Fermi paradox, has spawned countless theories, from the grim, like self-destructive tendencies common to intelligent life, to the fantastical. But what if the answer isn't about biology or sociology at all? What if the cosmos itself is hiding something? Consider this: advanced civilizations might not want to be found. Imagine a universe where intelligence evolves to a point where physical expansion becomes irrelevant. A species that masters quantum computing or harnesses dark energy could transcend the need for starships and radio towers, retreating into digital realms or higher dimensions, leaving the material universe as quietly as a child outgrowing toys. They might view our frantic broadcasting the way we'd regard smoke signals, quaint but hopelessly primitive. Or perhaps the universe conspires to keep civilizations apart. The vastness of space isn't just a barrier of distance, it could be a veil. Some theories suggest that dark matter's gravitational influence creates islands where life can flourish, separated by voids so immense that even light can't bridge them in time. It's like being on opposite shores of an ocean with no boats. We're not alone, but we're effectively alone. Then there's the unsettling possibility that we're simply early. The universe is 13.8 billion years old, but most stars and potentially habitable planets will form trillions of years from now. If intelligence tends to arise late in cosmic history, we might be the first flickers of awareness in a dawn that's barely begun. The silence isn't ominous, it's the sound of an empty theater before the show starts. But the wildest idea of all, we're missing the signals because they're encoded in ways we can't perceive. Neutrinos, gravitational waves, or even quantum entanglement might be the interstellar internet of advanced civilizations. Imagine ants crawling over a fiber optic cable, oblivious to the torrent of data passing beneath them. To species that communicate via space-time ripples or dark matter interactions, our radio telescopes might be as useless as tin cans on a string. Whether we're alone, ignored, or just tragically out of sync with the cosmos, the Fermi paradox isn't just a question about aliens, it's a mirror reflecting our own place in the universe. The silence might not mean no one's out there. It might mean we're not listening the right way, or worse, they've already answered and we're too young to understand. Glowing faintly in the pre-dawn or twilight sky, the zodiacal light looks like a celestial phantom, a cone of soft radiance stretching upward from the horizon. This eerie glow comes from sunlight scattering off countless dust particles drifting through the inner solar system. But here's the puzzle: there's far more dust than there should be. Based on the rate comets and asteroids naturally shed material, the cloud should have thinned out eons ago. So where's all this excess cosmic dust coming from? The answer might rewrite what we know about our corner of the galaxy. One leading suspect is a hidden population of dark comets' icy bodies lurking in the solar system's shadows, undetectable until they start decaying. These stealthy wanderers could be dumping fresh dust as they slowly disintegrate, replenishing the zodiacal reservoir. Then there's the interstellar interloper theory. Remember Oumuamua, that bizarre cigar-shaped object that zipped through our system in 2017? What if smaller visitors arrive constantly, breaking apart near the sun and leaving trails of alien dust in their wake? Our solar system might be swimming in galactic debris, the interstellar flotsam of countless distant stars, but the most tantalizing explanation ventures into the realm of the unseen. Some physicists speculate that dark matter, the mysterious substance making up most of the universe's mass, could be decaying right here in our cosmic backyard. Certain dark matter models predict particles that self-destruct over eons, releasing ordinary matter as they vanish. If true, the zodiacal light might be the shimmering signature of dark matter's slow demise, a faint glow born from the universe's greatest mystery. Of course, not all clues point to exotic origins. Recent simulations suggest violent collisions in the asteroid belt could be grinding rocks into dust faster than we thought, while Jupiter's gravity might be funneling debris inward like a cosmic conveyor belt. Yet even these conventional explanations come with twists, like the possibility that ancient mega-collisions, like the one that formed Earth's moon, left behind dust clouds that never fully settled. What makes this enigma so compelling is how close to home it lies. Unlike distant galaxies or abstract quantum realms, the zodiacal dust is literally in our front yard, yet still defies explanation. Whether it's comet crumbs, interstellar hitchhikers, or whispers of dark matter, this ethereal glow reminds us that even the familiar can hold profound secrets. After all, sometimes the biggest mysteries aren't hidden in the depths of space, they're floating right in front of us, catching the light. When NASA Pioneer 10 and 11 spacecraft sailed beyond the orbit of Pluto, scientists expected them to coast through the void with clockwork precision. Instead, something bizarre happened. These robotic explorers, humanity's first emissaries to the outer solar system, began slowing down ever so slightly, as if an invisible hand was tugging them backward. The deceleration was tiny, just a fraction of a nanometer per second squared, but over decades and billions of miles it added up. This drift, dubbed the Pioneer Anomaly, defied every conventional explanation, sparking debates that still simmer today. At first, engineers suspected mundane causes, maybe fuel leaks or thruster misfires, but the probe's trajectories were too consistent for random glitches. The slowdown pointed to something deeper, something fundamental. The leading theory, thermal radiation. Pioneer's nuclear power sources emitted heat unevenly, and photons bouncing off the spacecraft surfaces could have generated enough recoil to account for the drift. It's like holding a garden hose. The water streaming out pushes back against your hand. Calculations showed this effect might explain up to 80% of the anomaly. Case closed. Not so fast, because here's the twist. Even after exhaustively modeling every bolt and antenna, a stubborn fraction of the deceleration remained unaccounted for. That's when physicists started eyeing the possibility of new physics. One radical idea invoked modified gravity, the notion that Einstein's equations break down at extremely weak accelerations, like those experienced in the icy depths of the outer solar system. Proponents pointed to modified Newtonian dynamics, which tweaks gravity's rules to explain galactic rotations without dark matter. Could the same tweak apply to Pioneer's path? Critics dismissed it, noting that other spacecraft, like Voyager, didn't show similar behavior, but supporters countered. maybe Pioneer's unique design, its spin-stabilized, boxy shape, made it more sensitive to subtle gravitational quirks. Then there's the dark horse candidate, unseen matter. What if the probes were plowing through diffuse clouds of exotic particles or interacting with dark energy's repulsive push? The numbers didn't quite fit, but the allure was undeniable. After all, history's greatest breakthroughs often start with anomalies. Mercury's wobbling orbit hinted at general relativity. Cosmic microwave background glitches revealed the universe's acceleration. Pioneer's drift could be another such whisper, a clue to physics we've yet to imagine. The irony: by the time scientists seriously dug into the data, Pioneer 10 had fallen silent, its radio signals too faint to detect. The mystery might have lingered forever if not for a stroke of luck. Engineers rediscovered decades-old magnetic tapes buried in archives containing pristine trajectory records. Reanalyzing them with modern tools narrowed the gap, but the thermal explanation still isn't perfect. That lingering uncertainty is what keeps theorists up at night. Because sometimes the smallest discrepancies hold the biggest secrets, and Pioneer's ghostly drag might yet rewrite the rules of the cosmos. On the night of August 15, 1977, a radio telescope in Ohio picked up a signal so unusual that the astronomer who discovered it circled the printout and scribbled, "Wow." In the margin, a name that stuck. For exactly 72 seconds, a narrowband radio burst blared from the constellation Sagittarius, hitting a frequency near 1420 MHz, a range where cosmic noise is naturally quiet. Then, just as suddenly as it appeared, it vanished, never repeating despite decades of follow-up searches. The WOW signal remains the most tantalizing and frustrating hint of extraterrestrial communication ever detected. But what if we've been missing a crucial clue? What if the signal wasn't a one-off, but part of a pattern we're just beginning to decipher? The signal's frequency is the first breadcrumb. 1420 MHz isn't random, it's close to the hydrogen line, the resonant frequency of the universe's most abundant element. Hydrogen emits at 1420.4, making it a natural waterhole for interstellar communication. Any advanced civilization would know this frequency cuts through cosmic static like a beacon. But here's the kicker: the WOW signal's intensity spiked and faded smoothly, exactly as you'd expect if it were a focused transmission sweeping past Earth due to planetary rotation. That precision is hard to chalk up to natural phenomena. Pulsars, for example, pulse with metronomic regularity, while the WOW signal was a single, unmodulated burst, more like a deliberate shout than a cosmic hiccup. Then there's the direction. Sagittarius points toward the galactic center, a dense stellar hub where civilizations might cluster. But it also lines up with something far more intriguing: a pair of sun-like stars 220 light-years away. In 2016, astronomers identified these potential candidates, uncharacteristically solar twins, in the exact patch of sky where the signal originated. If an alien transmitter were targeting Earth, aligning itself with our Sun's spectral signature would be a logical starting point. Even stranger, 72 seconds matches how long the telescope's receiver would have been locked onto a fixed point in the sky. It's as if the signal was designed to be noticed by our technology, but not all clues point to aliens. Some researchers argue the signal could be a rare reflection, interstellar hydrogen bouncing off a passing comet's debris cloud, amplifying the natural hydrogen line into a fleeting spike. The problem: no known comet was in the right position that night. Others suggest it might have been a military satellite or secret Earth-based transmission, though no records match the frequency or power required. The most unsettling possibility: the signal was artificial but not meant for us. Imagine an interstellar navigation pulse or a long-dead civilization's final broadcast, sweeping through space like a ghostly SOS we happen to intercept. The real tragedy of the WOW signal is its silence. Without a repeat, we're left chasing shadows, but maybe that's the point. In a universe where light takes millennia to cross the void, patience isn't just a virtue, it's a necessity. The cosmos doesn't owe us answers on demand. Sometimes the most profound messages aren't the ones we hear, but the ones that leave us listening, wondering, and reaching for the stars. On the morning of June 30th, 1908, a fireball brighter than the sun tore across the Siberian sky, leveling 800 square miles of forest near the Tunguska River. The blast flattened 80 million trees in an instant, their trunks radiating outward like matchsticks from ground zero. Witnesses hundreds of miles away described a column of blue light splitting the heavens, followed by shockwaves that knocked people off their feet and shattered windows. For over a century, this event has stood as one of Earth's greatest cosmic mysteries, an explosion with the force of 1,500 Hiroshima bombs, yet leaving no crater. The absence of obvious debris has fueled wild speculation, with theories ranging from rogue antimatter to runaway Cold War experiments centuries ahead of their time. The most conventional explanation points to a stony asteroid or comet fragment vaporizing midair. But here's the catch: no trace of extraterrestrial material has ever been conclusively linked to the event. That glaring lack of evidence has opened the door to far stranger possibilities. Take antimatter, nature's most volatile substance. Just a grape-sized chunk colliding with normal matter could unleash Tunguska-level energy. Some researchers suggest a packet of antimatter, perhaps ejected from the galaxy's core or trapped in an ancient meteoroid, might have annihilated itself in Earth's atmosphere. The math works: antimatter reactions convert mass to energy with 100% efficiency, yet no telltale radioactive residues or gamma-ray signatures were ever found. Then there's the black hole hypothesis. Imagine a primordial mini-black hole, no heavier than a mountain but as small as an atom, zipping through Earth like a bullet through tissue paper. The gravitational tides alone would have superheated the air, triggering a titanic explosion. But here's the twist: such an object would have punched straight through the planet, exiting somewhere in the North Atlantic, yet no matching seismic or atmospheric event was recorded. Unless, of course, the black hole got stuck, orbiting inside Earth's core to this day. It's a wild idea, but one that cosmologists like Stephen Hawking once took seriously enough to investigate. The most chilling theories involve human intervention. Decades before the Manhattan Project, inventor Nikola Tesla boasted of wireless energy transmissions capable of splitting the globe. Some claim his Wardenclyffe Tower experiments accidentally unleashed an atmospheric resonance wave, focusing energy onto Siberia like a death ray. Declassified documents even hint at early Russian particle beam tests gone horribly wrong. The timing is suspicious. Tunguska occurred during peak solar minimum, when Earth's weakened magnetic field might have made the upper atmosphere unusually vulnerable to manipulation. While no hard evidence supports these claims, they linger in the shadows of classified research. Perhaps the truth lies beyond astrophysics entirely. Indigenous Evenki tribes spoke of the fire god Agdi descending that morning, a being of vengeance from their legends. Could Tunguska have been a rare cosmic alignment, a geomagnetic storm, ball lightning on a continental scale, or even a space-time rupture? The event coincided with peaks in both the Leonid meteor shower and solar cycle 24, hinting at forces we barely understand. What makes Tunguska so unsettling isn't just the scale of destruction, but the way it defies categorization. It's a Rorschach test for theorists. Everyone sees their own explanation in the scorched trees and absent crater. Whether a freak asteroid, a lab accident lost to history, or something stranger still, the event whispers a warning. The universe keeps its most explosive secrets hidden in plain sight. And sometimes the absence of answers is the most terrifying clue of all. Look up at the moon tonight and you'll always see the same familiar face, the same shadowy seas, the same crater-pocked plains. But flip around to the far side and it's a completely different world. one we never saw until spacecraft peered behind the lunar curtain in the 1960s. This isn't a cosmic quirk, it's called synchronous rotation, where the moon spins on its axis at the exact same pace it orbits Earth, forever keeping one hemisphere pointed our way. The odds of this perfect alignment happening naturally are astronomically low, yet here we are. So how did our celestial neighbor get locked in this gravitational embrace? The textbook answer is tidal locking, a slow dance of gravity and friction. Early in its history, the moon rotated faster, but Earth's gravitational pull created bulges in the lunar crust, like ocean tides but in solid rock. Over billions of years, the drag from these bulges acted like a brake, gradually slowing the moon's spin until it matched its orbital period. This phenomenon isn't unique. Many moons in our solar system are tidally locked to their planets, from Phobos around Mars to Pluto's partner Charon. But here's what makes our moon special. It locked incredibly fast. Most moons take tens of billions of years to synchronize. Earth's did it in just a few 100 million. That speed raises eyebrows. Some scientists point to a colossal impact, a second moon, perhaps, that once shared our sky before crashing into its sibling and jolting our moon into early submission. Others suggest Earth's ancient magma ocean, boiling with tidal forces, accelerated the process. But then there are the fringe theories, the ones that make you pause. What if the moon's synchronous rotation isn't natural at all? Enter the lunar anomaly crowd. They note how perfectly the moon obscures the sun during eclipses, a coincidence of size and distance so precise it feels engineered. They highlight the moon's unusually circular orbit, its bizarre lack of a dense core, and those strange transient lunar phenomena, flashes of light scientists still can't fully explain. Could these be clues to artificial origins, the wildest hypothesis that the moon isn't a natural satellite, but an ancient megastructure placed in orbit, its rotation deliberately set to keep one face forever hidden? After all, if you were building a cosmic observatory or a monitor, wouldn't you want to control what it sees? Of course, mainstream science dismisses this as fantasy. But the moon's mysteries persist. Why does its far side look so different? Thicker crust, fewer seas, as if shaped by forces we've yet to understand. And why, mathematically, does its presence stabilize Earth's tilt, creating the seasons that made complex life possible? Coincidences add up, and sometimes the universe feels less like random chaos and more like a puzzle waiting to be solved. Whether through brute physics or something stranger, the moon's eternal gaze reminds us that even the closest worlds guard their secrets well. In October 2017, astronomers spotted something unprecedented, a visitor from another star system tumbling through our solar system. Named Oumuamua, Hawaiian for scout, this interstellar interloper defied all expectations. Its elongated shape, tumbling motion, and most baffling of all, sudden acceleration as it slingshotted past the sun sent shockwaves through the scientific community. Was it just a weirdly shaped space rock or something far more extraordinary? At first, Oumuamua's acceleration seemed easily explained: comet outgassing. When comets warm up near the sun, they release jets of vaporized ice acting like natural thrusters. But here's the catch: no outgassing was ever detected. No tail, no coma, no dust cloud, just pure, unexplained motion. Some researchers proposed that Oumuamua's gases might have been trapped beneath an unusual surface layer, venting unseen. Others pointed to hydrogen ice, which could vaporize without leaving a visible trace. Yet even these theories felt like patchwork, straining to fit observations into known physics. Then came the bombshell. Harvard astronomer Avi Loeb suggested Oumuamua's acceleration might not be natural at all. Its trajectory and reflectivity matched what you'd expect from a light sail, a thin, flat object pushed by the pressure of sunlight like a cosmic kite. If true, Oumuamua could be artificial, a relic from an advanced civilization. The idea sparked fierce debate. mainstream scientists dismissed it as sensationalism, arguing that natural explanations, however incomplete, were far more likely than alien technology. Yet Loeb held firm: when nature fails to explain, we must consider all possibilities, no matter how unsettling. But what if the truth lies in the extremes of physics? Some theorists proposed that Oumuamua could be made of exotic matter, particles or structures unlike anything in our solar system. Dark matter fragments, cosmic strings, or even a rogue piece of a neutron star might exhibit bizarre acceleration without conventional outgassing. Others floated the idea of a fractal-like dust bunny, a porous aggregate of interstellar debris so light that solar radiation alone could push it. The problem: no known natural process creates objects like these. The real frustration is that Oumuamua is gone, fading into the cosmic dark before we could study it further. Future telescopes might catch more interstellar visitors, but for now the mystery lingers. Whether a shard of alien technology, a cosmic oddball, or something beyond our current understanding, Oumuamua challenges our assumptions about what's possible. Sometimes the universe sends us a riddle wrapped in stardust, not to taunt us, but to remind us how much we have yet to learn. At the solar system's frozen frontier beyond Neptune's orbit, something massive seems to be stirring the cosmic pot. The Kuiper Belt, a ring of icy debris left over from the solar system's birth, should be a predictable place with objects following orderly paths dictated by the known planets. But a handful of these distant bodies move in ways that defy explanation, their orbits oddly clustered and tilted as if an unseen hand is herding them. The culprit: a growing chorus of astronomers suspects a hidden world, Planet 9, a super-Earth up to 10 times the mass of our own planet, lurking in the darkness. Clues are written in the trajectories of extreme trans-Neptunian objects like Sedna and 2012 VP 113. These icy wanderers swing absurdly far from the Sun, some with orbits so elongated they take thousands of years to complete. Even stranger, their closest approaches to the Sun, their perihelia, cluster in roughly the same patch of sky. Statistically, the odds of this happening randomly are about 1 in 14,000. It's as if something massive, with a gravitational reach spanning hundreds of astronomical units, is nudging them into alignment, but hunting an invisible planet is no easy feat. Unlike the serendipitous discovery of Neptune found in 1846, after mathematicians predicted its position based on Uranus's wobbles, Planet 9's potential orbit is staggeringly wide. It could take 15,000 years or more to circle the Sun, meaning it might currently be hiding anywhere along a colossal celestial highway. To make matters trickier, such a distant world would reflect almost no sunlight, leaving telescopes searching for a needle in a cosmic haystack. Critics argue the evidence might be an illusion, an artifact of observational bias. Most Kuiper Belt surveys focus on specific regions of the sky, potentially creating false clusters in the data. Others propose that collective gravity from smaller, undiscovered objects could mimic the effect of a single large planet. Yet simulations suggest this scenario is unlikely. It would require an implausible amount of unseen mass scattered just right to sculpt the orbits we see. The most tantalizing twist: Planet 9 might not be alone. Some models hint it could have siblings, rogue planets captured from other stars during the solar system's chaotic infancy. Or perhaps it's not a planet at all, but a primordial black hole no larger than a grapefruit, warping space-time with its immense density. Whatever the truth, the hunt has already reshaped our understanding of the solar system's edges. Every anomalous orbit, every odd alignment, is a breadcrumb leading deeper into the dark and closer to rewriting the map of our cosmic backyard. What if the universe isn't just a cold, mechanical expanse, but a vast, self-regulating system, alive in ways we're only beginning to grasp? That's the radical heart of the Gaia hypothesis scaled to cosmic proportions. On Earth, the Gaia theory proposes that our planet's biosphere acts like a living organism, with oceans, atmosphere, and life itself locked in delicate feedback loops that maintain conditions for survival. Rainfall adjusts to stabilize temperatures, microbes modulate greenhouse gases, but extend this idea beyond our pale blue dot, and something extraordinary emerges. A universe where galaxies, black holes, and even the vacuum of space might be part of a grand, self-balancing act. Take dark energy, for instance. Its mysterious acceleration of cosmic expansion seems finely tuned too weak, and the universe would have collapsed eons ago, too strong, and galaxies would tear apart before life could arise. What if this isn't luck but a kind of cosmic homeostasis? Some theorists suggest that dark energy could be a regulatory mechanism, a universal thermostat adjusting expansion to preserve structures capable of complexity. Even black holes, those infamous destroyers, might play a role. Their voracious feeding could recycle energy into star-forming regions, like cosmic gardeners pruning and fertilizing the galactic ecosystem. The math hints at eerie parallels. Just as Earth's carbon cycle balances emissions and absorption, the universe's matter-antimatter asymmetry might reflect a deeper equilibrium. Why is there something rather than nothing? Perhaps because the cosmos prefers states where structure can persist. Even the vacuum's energy, the so-called zero-point field, fluctuates in ways that eerily resemble biological feedback systems, damping extremes to maintain stability. Of course, critics dismiss this as poetic thinking. They argue that apparent fine-tuning is just selection bias. We observe a universe that allows life because we're here to observe it. But Gaia's cosmic proponents counter that the sheer scale of harmony, from quantum fields to galaxy clusters, demands more than anthropic luck. If Earth's biosphere can self-regulate, why not the universe? After all, fractals teach us that patterns repeat across scales. Why not the pattern of life itself? The most tantalizing possibility: consciousness might be part of the loop. Just as trees pump oxygen into Earth's atmosphere, sentient observers could influence quantum probabilities through measurement, nudging reality toward stability. It's a dizzying thought that the universe isn't just observed but shaped by the act of observation, a vast, self-aware dance of energy and information. Whether science or philosophy, one thing's clear: the cosmos hums with rhythms we're only starting to hear. And if Gaia's whispers are real, the universe isn't just our home. It might be alive. We've all experienced it, that eerie moment when you swear something happened a certain way, only to find out history disagrees. Maybe you remember Nelson Mandela dying in prison in the 1980s, or the Monopoly man wearing a monocle, or the Berenstain Bears spelled with an E. These shared false memories, known as the Mandela effect, are more than just quirks of the human brain. What if they're glitches in reality itself, fleeting glimpses of parallel timelines bleeding into our own? At first glance, the Mandela effect seems like a simple case of misremembering. Human memory is famously fallible, stitching together fragments of experience into shaky narratives. But the sheer number of people recalling identical details, down to specific dates, spellings, or imagery, raises unsettling questions. Why do so many remember the same, wrong version of events? One spine-tingling possibility is that these discrepancies aren't errors at all, but residues of alternate realities where things truly were different. Quantum physics offers a potential framework, the multiverse theory. In this view, every decision branches into new timelines, creating infinite variations of history. Normally, these worlds remain separate, but what if they occasionally overlap or collide? Decoherence, the process that keeps quantum possibilities from interfering with our classical reality, might not be perfect. Tiny leaks between timelines could imprint fragments of other histories into collective memory, leaving us with a sense of dissonance, a hunch that reality has been edited without our consent. Some researchers point to the Large Hadron Collider as a potential catalyst. Could high-energy particle collisions briefly weaken the barriers between dimensions, allowing information from adjacent timelines to slip through? Others speculate about cosmic phenomena, solar flares, black hole mergers, or dark matter interactions that might temporarily fray the fabric of space-time. Even consciousness itself could play a role. If observation truly shapes reality at the quantum level, as the Copenhagen interpretation suggests, perhaps mass human focus on certain events like Mandela's death creates feedback loops that nudge timelines closer together. Skeptics, of course, have simpler explanations. Social contagion and the power of suggestion can warp memories en masse. The internet amplifies these effects, reinforcing false narratives through repetition. And some false memories, like the monocle on Mr. Peanut, often conflated with the Monopoly Man, stem from legitimate cultural mashups. But the timeline's theory persists because it taps into a deeper unease. That reality isn't as solid as we think. Whether through quantum flux, cosmic accidents, or something stranger, the Mandela effect forces us to confront the unsettling idea that the past might be as malleable as the future. And if that's true, what else have we all misremembered without realizing it? Hidden in the depths of abstract mathematics lies a numerical structure so bizarre, it might just be the universe's best-kept secret. Meet the octonions, an 8-dimensional number system where multiplication isn't just unpredictable, it's downright chaotic. Forget the tidy rules of everyday arithmetic. Here, the order in which you multiply numbers changes the outcome, like a cosmic game of musical chairs where the seats rearrange themselves mid-spin. At first glance, these mathematical oddities seem like little more than a curiosity, the kind of thing only theorists would lose sleep over. But dig deeper, and you'll find octonions lurking in the most unexpected places, from the symmetries of string theory to the very fabric of spacetime itself. What makes octonions special isn't just their complexity, but their exceptional nature. In mathematics, certain structures are so rare, so perfectly tuned, they're labeled exceptional. The octonions belong to this elite club, sitting alongside only a handful of other mathematical objects that defy conventional classification. Their symmetry, the way they rotate and interact in abstract space, mirrors patterns seen in particle physics, particularly the behavior of quarks and leptons. Some theorists suspect this isn't coincidence. The Standard Model, our best map of fundamental forces, has gaps that conventional math struggles to fill. Octonions, with their intricate dance of dimensions, might be the missing key, offering a unified language for forces that currently seem unrelated. String theorists were among the first to take notice. In the quest for a theory of everything, octonions pop up naturally in certain higher dimensional frameworks, hinting at a deeper order beneath the quantum chaos. Even more tantalizing, the symmetry groups formed by octonions align eerily well with the Lie groups used to describe fundamental particles. It's as if the universe's building blocks are whispering in octonionic code, waiting for us to crack the cipher. But the wildest idea comes from those who see octonions not just as tools, but as architecture. If spacetime isn't just four-dimensional but somehow octonionic at its core, our perception of reality might be a shadow cast by these 8-dimensional gears turning behind the scenes. Imagine gravity, electromagnetism, and the nuclear forces not as separate phenomena, but as different facets of a single octonionic symmetry, fractured into pieces by the limitations of our 3-dimensional perspective. Skeptics argue that octonions are too abstract to have real-world relevance, a beautiful mind game with no experimental foothold. Yet history teaches us that the most profound breakthroughs often start as mathematical curiosities. Quantum mechanics once seemed equally esoteric until it revolutionized technology. Whether octonions remain a niche fascination or unlock the next physics revolution, one thing's certain: the universe loves a good pattern. And if its deepest secrets are written in a numerical dialect we're only beginning to learn, the octonions might be our Rosetta Stone. For decades, a shadowy object lurking in Earth's orbit has fueled wild speculation that we're not alone and never have been. Dubbed the Black Knight satellite, this enigmatic artificial structure supposedly dates back over 13,000 years, an alien surveillance probe silently circling our planet since before the pyramids. The legend is intoxicating. Radio operators in the 1920s picking up strange echoes, astronauts spotting mysterious debris during early spaceflights, even NASA images showing a bizarre, angular shape against the curvature of Earth. But peel back the layers and you'll find a story less about extraterrestrials and more about how easily the human mind stitches chaos into narrative. The myth's origins trace back to 1954, when newspapers reported two mystery satellites orbiting Earth, impossible at the time, since Sputnik wouldn't launch for another 3 years. Later, ham radio enthusiasts intercepted odd signals they claimed came from an ancient spacecraft. Then came the clincher, grainy 1998 footage from the Space Shuttle Endeavour, appearing to show a jagged, artificial object adrift near Earth. Conspiracy theorists pounced, insisting this was proof of pre-human technology, perhaps left by the same beings who inspired our ancestors' star myths. Reality, as usual, is less glamorous. The Black Knight isn't a singular object at all, but a mishmash of misidentified phenomena, those 1950s reports. Likely miscommunications about high-altitude research balloons or military projects. The eerie radio signals, natural pulsars or early satellite tests, their origins lost to Cold War secrecy. As for the infamous Endeavour footage, it captures nothing more exotic than a discarded thermal blanket, its crumpled edges catching sunlight at uncanny angles. Space debris tells its own fascinating story, over 34,000 tracked fragments hurtling overhead, some dating back to the dawn of the space age. But why does the Black Knight myth persist? Psychology offers a clue. Humans are pattern-seeking creatures, hardwired to spot faces in clouds and messages in static. Combine that with our cultural obsession with ancient astronauts, and even mundane space junk transforms into something mythic. The irony, in our eagerness to find alien watchers, we ignore the very real marvels above us, thousands of functioning satellites, the International Space Station, even Elon Musk's Starlink trains painting the night sky. The truth may not be as thrilling as a 13,000-year-old probe, but it's no less extraordinary. We've turned Earth's orbit into a bustling highway of human ingenuity. And if there are aliens out there, they'd probably be more impressed by that than any rusty old relic. Here's something that should boggle your mind: dark energy, the mysterious force accelerating the universe's expansion, and dark matter, the invisible glue holding galaxies together, have nearly identical densities right now. Not a billion years ago, not a trillion years in the future, but today, in this fleeting cosmic moment we happen to inhabit. The odds of this coincidence are astronomically slim, like tossing a coin and having it land perfectly on its edge every single time for billions of years. This is the cosmic coincidence problem, and it's one of the most perplexing fine-tuning puzzles in modern cosmology. So why does this alignment feel so convenient? One school of thought leans into anthropic reasoning, the idea that we observe these precise conditions because they're the only ones that allow our existence. If dark energy had dominated earlier, galaxies would have been ripped apart before stars could form. If dark matter had been too sparse, gravity couldn't have sculpted the cosmic web that birthed us. In this view, the coincidence isn't random. It's a prerequisite for life, a selection effect in an infinite multiverse where only the habitable universes get observers. But this explanation leaves some scientists cold. It feels like shrugging and saying, things are this way because otherwise we wouldn't be here to ask. That's where cyclic models come in, offering a more dynamic solution. Picture the universe not as a one-and-done Big Bang, but as a phoenix eternally reborn. In these theories, dark energy's current dominance isn't permanent, it's a fleeting phase in a grand cycle. Each iteration begins with a collision or bounce, expands until dark energy thins out, then contracts or collides anew, resetting the cosmic clock. The magic here is timing. Dark energy and matter densities naturally intersect at regular intervals, like hands on a clock briefly overlapping. We're not special, we're just living during one of those inevitable intersections. But there's a wild card. What if dark energy isn't constant at all? Quintessence models propose it's a dynamic field, ebbing and flowing over time. If its strength evolves, the coincidence might be an illusion, a temporary snapshot of a deeper, slower process. Imagine watching a pendulum swing past the midpoint. If you blinked at just the right moment, you'd think it paused there magically. Similarly, dark energy's current balance with matter could be a fleeting equilibrium in a much larger dance. The stakes couldn't be higher. If the coincidence is real, it might hint at new physics, a fundamental link between dark energy and dark matter we've yet to discover. If it's an illusion, our entire understanding of cosmic evolution could be upside down. Either way, the universe is whispering a riddle, and the answer might rewrite not just our future but our past. Because if conditions aren't coincidental, then time itself could be playing tricks on us, hiding patterns deeper than we've dared to imagine. Time itself might not be the endless river we imagine. What if it's more like a fading echo, destined to dissolve into silence? The end-of-time theory paints a chilling vision of the universe's ultimate fate, where the cosmos doesn't just cool and darken, but where the very fabric of duration unravels. Picture heat death, that distant era when all stars have burned out, black holes evaporated, and the universe reaches perfect thermal equilibrium, a state of maximum entropy where no energy flows, no change occurs. In this frozen tableau, time loses all meaning. No cause precedes effect, no before gives way to after. The universe becomes a static, patternless snapshot, a single moment stretched into eternity. This isn't just poetic nihilism, it's rooted in the physics of entropy. In thermodynamics, time's arrow is tied to increasing disorder. As the universe approaches equilibrium, the arrow weakens. Without temperature differences to drive motion or information gradients to sustain computation, even the most resilient structures, atomic nuclei, protons themselves eventually decay. What remains is a sea of photons and fundamental particles, spread so thinly that no two interact across the cosmic void. In this state, the distinction between one instant and the next blurs into oblivion. But here's the twist. Some theorists argue that time's cessation doesn't equate to oblivion. Without change, there's no way to measure duration, but the universe's final configuration, its ultimate moment, could persist unchanging, eternally present. It's a paradox. Time ends, yet the universe endures, frozen like a bug in amber. Think of a paused movie frame. The image exists, but the story ceases to progress. This static reality might even loop, with quantum fluctuations in the infinite future, occasionally resurrecting fragments of structure in a phenomenon called Poincaré recurrence. The same arrangements of particles could reappear, not as true rebirth, but as echoes in the dark, like a broken record replaying the same note forever. Critics counter that this ignores quantum gravity's unknowns. Could space-time itself, absent of matter and energy, retain some primordial structure? String theory suggests that even in emptiness, the geometry of extra dimensions might persist, hinting at a deeper substrate beneath time's illusion. Others propose that consciousness, if any remains, could impose a subjective sense of duration, no matter how frozen the cosmos. The end-of-time theory forces us to confront the fragility of existence. Everything we cherish, memory, progress, even the ticking of a clock, relies on time's flow. Strip that away, and reality becomes a single, silent painting hanging in the gallery of nothingness. Whether it's the universe's true finale or just another chapter in a grander cycle, one thing's certain: time's finale won't be an ending, but a transformation so profound we lack the words to describe it. And perhaps that's the most haunting clue of all, that the cosmos reserves its deepest mysteries for when the clock finally stops. From the Fibonacci spirals etched into galaxies to the holographic code that might underpin reality itself, the universe is teeming with patterns that refuse to fit neatly into our textbooks. These aren't just cosmic quirks, they're breadcrumbs leading us toward truths far stranger than we ever imagined. Think about it. Black holes that could be gateways to other dimensions, dark matter weaving an invisible web that sculpts the cosmos, or even the spine-chilling possibility that we're living in a simulation where the rules are written in some alien programmer's code. Each of these theories isn't just a wild guess, it's a response to the universe's nagging whispers, the anomalies that poke holes in our comfortable understanding of reality. What makes these ideas so electrifying isn't just their audacity, but how they force us to confront the limits of human perception. We're like ants trying to map a cathedral, glimpsing only fragments of the grand design. The golden ratio might be a hint of a deeper mathematical language, while the cosmic microwave background's eerie cold spot could be a bruise from a collision with another universe. Even time itself, that steady arrow we take for granted, might be an illusion, a fleeting phenomenon destined to dissolve into silence. The more we learn, the clearer it becomes. The universe isn't just hiding secrets. It's daring us to think bigger. Now, here's where you come in. Which of these theories bends your mind the most? Is it the holographic principle, with its dizzying suggestion that reality is a 2D projection? Or the Boltzmann brain paradox, which makes you question whether your memories are even real? Drop your thoughts in the comments. I'm itching to hear which cosmic mystery keeps you up at night. And if you're hungry for more deep dives into the universe's hidden blueprints, hit that subscribe button. Because trust me, we've only scratched the surface. The cosmos has a way of out-weirding our wildest ideas, and the next revelation might be just one click away. Until then, keep looking up and questioning